All right, I'm going to skip this because we have to get on to more important things. Sketching graphs, doing the reflection thing. Yeah. All right. Okay. More properties about the log. If I take the log of a product, it's the sum of the logs. So a log turns a product into a sum. And here, of course, for this to be true, everything has to be well defined here. So x and y both have to be positive for you to use this. This is called the product rule. We have a similar quotient rule. The log of a quotient is the difference of the logs. So it's log of the numerator minus the log of the denominator. So that's called the quotient rule. And the power rule is if you take the log of x to some exponent r, then that's the log of x times r. So you can take the exponent and sort of bring it outside and multiply it on the outside. And then you get the same thing. And this is true for any r, for any real number r whatsoever, but any positive x, because this thing has to be well defined. So this is just illustrating. I'm going to have to skip this. Because I'm running out of time. All right, let's do an example of here. Suppose that you're given that the log to the base b of 2 is equal to u, and you don't know what b is, and you don't know what u is, but you just know that they satisfy this equation. Okay? And you know that the log to the base b of 3 is equal to b. Same b. Then can you express the log to the base b of 6 in terms of u and v? So here's what you're going to do. You're going to use the fact that 6 is 2 times 3. And then you're going to use the product rule. So log of 2 times 3 is log of 2 plus log of 3. Be very careful that you make this a plus. So a common mistake is to take that the log of a product is the product of the logs. That's not true. It's the sum of the log. So this is log to the log of 2 plus log of 3, but you already have that this thing is equal to u and that thing is equal to v, so that's just u plus v. So that expresses log of 6 in terms of u and v. How about log of 8?
Just 2 times 2 times 2.
It's 2 times 2 times 2, and you could use the product rule twice. Yeah. Or you could do it log 2 to the power of 3, right? And then you'd use the power rule. So let's do it the second way because that's what the slide said. We know the first way is correct. The 2 times 2 times 2. So here, you take the exponent and you move it to the outside. So 3 times log of 2, and log of 2 is u, so this is 3u. Let's do one more of these. 18. So 18 is, well, it's 6 times 3, it's 2 times 9. It's 2 times 9. That's what the slide says. So you could use the product rule to start with. And this is log 2 plus log of 9. But I only know what log 3 is. Yeah, so 9 is 3 times 3. So either using the product rule or the power rule, which says it's 3 squared, you get the same answer. The 2 comes out, and you get 2 times log of 3, so that's going to be u plus 2v. All right, do you think you can do these? I ask you to.
I'm going to try.
All right. So going on. So you could just, this is more practice using these properties. You can simplify big expressions in here involving products. So, for example, here, log of this hairy thing in here is just keep applying these properties until you can't apply them anymore. So you could take the log of 4x cubed plus the log of x minus 1. Log of 4x cubed is log of 4 plus log of x cubed plus, now bring that down. Well, base 2, so 2 squared is 4, so this is just 2. And then the power rule on this one gives me a 3 log 2 of x plus log of 2x 1. Can I do anything more than that? Yeah. Well, I can't do anything more with that because that's just an x. Can't break that any further. Here I have an x minus 1. No. There is no sum rule for logs. There's only a product rule. So the log of a sum or a difference, you can't simplify. You just can't. Unless you can factor it somehow. If you can maybe express it as a product or a power, that's fine. But otherwise, you can't do anything. So that's it. That's the final answer. It's the best exact answer you get. I gotta skip over this. More of the same. This is not as important as what's coming up. Is that my computer doing that?
It's built into the animation. So
Oh, is it?
As soon as we hit it, you'll hear it too.
Oh, okay. Maybe. Okay. I guess when I made these slides, I usually just by default have the sound off. I just turn the sound off because I'm usually like on a plane or something, or somebody's sleeping nearby. So, all right, I don't notice that these things are there. I appreciate it if you're making them. Please turn the sound off. Bless you. All right. Use logs to solve the equation. 10 to the power of x is 35. Hit both sides with a common log. That'll do it. And so x is the common log of 35. And I suppose you can expand this as 5 times 7, but that's not really simplifying it. That's expanding it. So maybe just leave it like that. If you want an approximate answer, go to your calculator, which you've got to update to that. It's about 1.54. And I'm going to have to skip over this one. All right, let's do this one. So 4e to the minus 0.05t. So here the variable's t, you want to solve for t. Minus 5 is equal to 19. Well, isolate the exponential on one side. So add 5 to both sides, and I get 24. Now, what? What would you do? Divide by 4. Yeah, divide by 4. Okay. So I get that is equal to 6. Now you've got a pure exponential on that side. So hit both sides with what? The natural log, yeah. Log to the base e. So that, because those are inverses, that will cancel out the exponential on the left, and I get natural log of 6 on the right, using that. So now solving for t, I just get the exponent here. So solving for t, I just divide by minus 0.5, which is minus ln of 6 over 20, if you prefer. And that's about 35.8. And I'm going to, okay, 2 to the x over 3 is equal to 15. Well, x over 3, hit both sides with a log to the base 2. Gives me x over 3 is log to the base 2 of 15. So multiply both sides by 3. X is 3 log 2 of 15. Well, what's that approximately equal to? Do you know how to do logs to any base in your calculator? No? Okay. There's a way to do it, but stop for a second, because I am biased against using calculators, because that's just how I grew up. I like pencil, paper, and brain. So most calculators that were around 20 years ago only allowed you to do natural logs, and maybe common logs. So, do a log to the base 2, you had a problem. All right, how do you do a log to the base 2? Well, it turns out there is a formula to convert from one base to another in logs. And that's what we're going to do right now. Well, actually, maybe I'll skip the derivation, but here's how you do it. Suppose you only had a natural log button. You only had an ln button on your calculator, and you wanted to solve this. How would you do it? Well, you take the natural log of both sides. You can't use log to the base 2 because your calculator won't handle it. So use the log that you have. Hit both sides with it. This is only if you're finding a decimal approximation. If you're computing an exact value, use log to the base 2 because that will give you an exact value. But if you take the natural log of both sides, you can still work this because you get the natural log of 15 on the right, and on the left, what does that do? What can you use now? The power rule. Exactly. So these don't cancel because the bases are different. You've got 2 and you've got e. They're not the same, so you can't cancel. But you can use the power rule, which says you can pull out the x over 3 outside. So this x over 3 times the log of 2 is log of 15, natural log. So x is 3 times the natural log of 15 divided by the natural log of 2. You solve for x. Okay. Now you can punch the right-hand side into your calculator and get it. If you only had a natural log button. And you get about 11.7. Okay. Well, you can do that thing in general to get a change of base formula. And to use the power rule, use the inverse rule, and I'm not going to explain this because I want to short on time. But here is the change of base rule. If your calculator or program can compute logs to the base b, and you want to compute the log to the base a of something, here's what you do. You just take the log to the base b of x divided by log to the base b of a. So here's log to the base a on the left, expressed in terms of log to another base on the right. Okay. So that's the change of base formula. So in principle, you can compute logs to any base, if only you have one base. So I got to skip the example. All right, let's do an application of these functions. Compound interest. So this is a more detailed version of the bank account we talked about earlier. You have some principal P. This is an amount of money you initially invest in an account. And the interest rate is S. That's going to yield an interest of S times P. So here, P is some monetary amount, say in dollars. And S is just some unitless real number. It's like 0.1 or something like that. This is the amount of interest you get. You typically take that interest and just add it to the account. So the new amount is going to be P plus the interest. So it's P plus S times P, or P times the quantity 1 plus S. So if you compound the interest once, that's what you get. So that's your new amount. So compound it once, you're just multiplying by 1 plus S. If you then later on compound it again, you're taking that thing, the new amount, and multiplying it by 1 plus S. So after, say, m compounding periods, what you're doing is the amount accumulated after n periods is going to be P times the quantity 1 plus S to the power n. Okay. So we think of S as being fixed, and n as being the variable. This is an exponential. This is an exponential function of n. So if P equals 100, S is 15%. A is going to be 100 times 1 plus 1, 5 to the n, okay, for n periods. So here's a graph of the amount plotted against n, the value n, or value x rather. It's an exponential function. Now you can ask questions about it. For example, when will A exceed 1600? Well, what you do is you solve this. Basically, you want to know how many periods go by before this thing exceeds 1600. So you set this equal to 1600 and you solve for n. This is solving an exponential equation. So divide both sides by 100, and you get 1.15 to the n is equal to 16. Now, you could hit both sides with the natural log because that's what your computer can handle. That's what your calculator can handle. Use the power rule on this side, and you get n times the natural log of 1.15 is the natural log of 16. Divide that, and you get n is equal to this, and that you can plug in your calculator, and you get about 19.8 periods. Now, this is discrete compounding, so there is no fractional number of compound periods. So the time you're going to actually exceed this amount is on the next period, which is going to be 20th period. So you round up to the next integer. So after 20 periods, that's when you're going to exceed $1,600. All right. So instead of S, which is the interest rate per period, we usually express the interest rate per year, called the annual interest rate or the annual percentage rate or APR, together with the number of periods per year. So we'll call the annual interest rate, the APR, we'll call that R. The number of periods per year we'll call M. And now S is going to be the ratio. This is the interest rate per year divided by the number of periods per year. So this is the interest rate per period. It's R over M. That's equal to S. So substituting R over M in for S over here gives you this equation for the amount. It's P times the quantity 1 plus R over M to the power, well, here, after 1 year, there are M periods in 1 year. So you take that to the power M. That gives you the amount after 1 year. After 2 years, there are going to be 2 M periods. And in general, after T years, there are going to be that many periods, M times T. So this is the general form for discrete compounding for some M periods per year times the number of years, T. So, for example, well, if I start with the principal of $2,000 at an APR of 5%, compounded semi-annually, or quarterly, or monthly, or daily, or hourly, well, the principal is $2,000. T is equal to 1. Because that's 1 year. And R is the annual percentage rate. That's 5%, so that's 0.05. The only thing that's changing here is M. So if it's semi-annually, what's M? 2. Quarterly, it's going to be 4. Monthly, it's going to be what? 12. 365. Hourly, something. A lot. Okay. So here's the formula if I just plug in everything else besides M. All right. Now I've got this. So if, all right. There we go. So this is the amount after 1 year. So if I take X and Y1, so what is X? What is X here? Sorry, this should be, sorry, that's a mistake. This should be M. Okay. That's M. M is 2. If you plug 2 in here and you crunch the numbers here, you're going to get 21.01 and 25 cents. That's you started with 2,000 and now you've made about $100, a little bit more. If M is 4, you expect to get some more because you're compounding more frequently. But notice you don't get a whole lot more. You only get about 65 cents more. Then this 12, you get a little bit more, not much. And this 365, you get a little bit more than that. And then this hourly, you get a tiny bit more, maybe even just a cent, give or take. So compounding much more frequently is not really giving you a huge increase in the amount you get. And in fact, you might suspect that this is actually approaching a limit. As m goes to infinity, these numbers actually approach a limit. Okay. And the answer is yes. If as m goes to infinity, this actually approaches a limit, and I am going to skip the derivation of this, and I'm going to just jump to the conclusion here. Here's right here. If you're essentially compounding every instant, okay, that's the limit as m goes to infinity. This is the formula for how much you have after t many years. Now notice there's no more m, right? This is called compounding continually or continuously. You get a very simple formula. You take the principal, take the interest rate times the number of years, take e to the power of that, and multiply by the principal. That's your amount. And if you do that, here's what you actually get. You get 2102, 54 cents, and 54.22 cents to that. So that is in fact the limit. So in fact, it's just a tiny bit more than this. Okay. So this is called compounding. This is compounding m times a year. This is compounding continuously. This formula is much easier for banks to use than discrete compounding. So once computers came along, banks switched to continuous compounding. The thing about continuous compounding is you don't actually have to compound the interest every period. You just wait until there's another transaction on the account, look at the elapsed time from the previous transaction, see how much more money there is according to that formula, and just add it in. That's it. So you only recompute the amount every time there's a transaction. Okay, and it's very easy to do. Okay. So questions I might ask about this is I might give you some of these numbers, so 3 of these 4 parameters and not the 4th, and you have to solve for the 4th. Okay, and any one of these might be the thing you have to solve for. So just keep that in mind. All right. Now I'm going to skip this example as well. It's really the same idea. All right. Here's what we need to get to, and because this is much more important for y'all in terms of what you're going to see later on in this program you're in. Signal strength. So lots of physical quantities are measured in what are called logarithmic scales. And signal strength is one of them. The reason is because signal strength can vary extremely widely. And using the absolute value of the signal tends to be unwieldy because the numbers vary so widely that people instead tend to use a logarithmic scale where they take the log of the signal strength and use that as it's called the signal level. And they use that instead of the actual strength. And so a natural unit of signal strength is called the bell. This was named after Alexander Graham Bell. It's a logarithmic unit. And what it does is it describes a ratio. If I have two signal strengths, say N1, N2, and N1, I take the ratio, I take the log of that. That's called the difference. That's called the level difference in bells of the two signals. So these signals might be acoustic signals, they might be sound waves, they could be electromagnetic signals, they could, they could be seismic waves, they could be lots of things. So this is useful if these ratios tend to be very large. When ratios tend to be very large, then they could also be voltages, they could be power, they could be amps. Taking the log sort of tames that off because the log function increases very slowly. So it's useful to express these in a logarithmic scale. So much more common is not the bell, but is the unit of 1/10 of a bell. A 1/10 of a bell is called a decibel. Deci means 1/10. So a decibel is 1/10 of a bell. So that if this is the number of bells, the number of decibels is going to be 10 times that, because the decibels are smaller. So the number of decibels corresponding to this ratio is going to be 10 times the common log. So we take log to the base 10, the common log of this ratio. So dB is much more commonly used than the actual bell. And the word level, signal level, sound level, voltage level, whatever, is usually associated with the decibel unit. So let's do an example of sound levels. So we're going to use a decibel measure of the strength of a sound signal. So to do that, I here, this is a capital I, it's not a 1. I here is the intensity of the signal we want to measure. And we always have to take a ratio of two things. So what we do is we usually agree on some reference intensity, which we call I0 or I0. And we divide by I0. So doing that will give us a definite value beta for the decibel level of the signal. You take I divided by the reference intensity, take the common log, multiply that by 10. That gives you the level in decibels. So let's do an example. So the reference intensity is actually arbitrary. So the choice of I0 is arbitrary. It's usually chosen by some kind of general agreement. So there might actually be standards conventions where internationally people come and decide that we're going to use this value for I0 because it's some kind of natural value. But there's no mathematical reason to choose one value over another. But notice that the reference intensity itself has a decibel level of 0. Because if you take I0 divided by I0, you get 1. The log of 1 is always 0. So this is called the 0 point. So setting the 0 point is the same as setting the reference intensity. You're agreeing internationally that this value is going to be 0 decibels for this particular signal. All right. Standard reference intensity for sound through air, so acoustic waves through air, is chosen to be this: 10 to the minus 12 watts per square meter. So here the units are watts. Watt is a unit of power. It's the amount of energy being transferred per unit time. So it's usually expressed in joules per second or ergs per hour, something like that. And this is the amount of power going through an area like a window that's 1 square meter. So, you have a window that's 1 square meter and you're getting a certain amount of wattage coming through. That's a measure of the intensity. So if you expand the window to 2 meters by 2 meters, you get it's the same intensity of the signal. You're going to get 4 times the amount of power going through that area, but now your area is 4 times as big. So that's going to be the same. It's the same intensity. So it turns out this is near the limit of human audibility. That's why it's chosen. So this is right at about the limit that an average human can hear this. So that's why I think that's why it was chosen. It's also chosen to be roughly to be an exact number, some power of 10 times these agreed upon units, metric units. So let's suppose a whisper at 1 meter away is measured to be 10 to the minus 10th watts per meter squared. What is the sound level for this? It's a typical question that you would have to solve. Well, here's what you do. You plug these values in to get beta. So the top is the intensity you're interested in. This is the whisper. This is the reference intensity. Well, the units all cancel because they're just, the watts cancel and the meters squared cancel. All that goes away. So you're just left with 10 to the minus 10 divided by 10 to the minus 12. Okay. So 10 to the minus 10 divided by 10 to the minus 12. Well, that's 10 to the minus 10 times 10 to the 12. Which is 10 to the 12 minus 10, using that basic fact. So that's 10 squared. So that ratio is actually 10 squared, which is 100. So you take the common log of 10 squared, inverse functions, they cancel, you're just left with 2. So 2 times 10 is 20 decibels for the whisper. So the whisper is 20 decibels. Okay. Questions? Yeah.
If you asked us a question like this on the test, would we be expected to know what the I naught is? Or would that be given?
That would be given to you.
Okay.
I wouldn't ask you to remember that, no.
Okay.
Somehow, I'd either give it to you explicitly on the question, or you'd have some kind of reference thing you could look up to find it.
Okay.
Yeah. But the final exam is open book, open notes, so you have access to any printed material you want. You can also use your computers to look at slides. Really, the only thing you can't do is use your computers to actually compute. Or to surf the web or send or receive email. Okay. Any kind of communication that you would do with your computer, you can't use. But viewing slides, viewing any printed material is fine. So you can use it as an e-reader. All right. So we often compare two signal intensities directly. So in this case, if I have two signal intensities, what we're interested in is what is the difference in level between the two. Here's how you get the difference in decibel level between the two. You take their ratio. You take the ratio of intensities and apply the decibel formula to that. So it's going to be 10 times the common log of their ratio. To see why that's true, if I start with the ratio, if I start with what I said, the ratio, well, I can divide both the numerator and denominator by the reference intensity. Doesn't change anything. Now I apply the quotient rule to this, and I get 10, and distribute through by multiplying by 10. I get 10 times the log of I2 over I naught minus 10 times the log of I1 over I naught. These are now expressed as ratios using the reference intensity I naught. So this gives you beta of I2 and beta of I1, and it's the difference. So to get the difference in decibel levels, if you want to compare two sound or signal levels directly, you can just do it by taking their ratio. And that means you only have to take one log. You don't have to take a log once instead of twice. Okay, so the difference in signal levels corresponds to the ratio of their intensities using the common log. All right, so let's do an example. So the sound level of a jet engine at 50 meters away is about 130 decibels. the average threshold of pain is about 120 decibels. So this is 10 decibels above that. Now, if it's 10 decibels above that, what does that mean in terms of the intensity? Every time you go up 10 decibels, that's 1 bell. The log increases by 1, which means you are multiplying the intensity by 10. So the intensity of 130 decibels is 10 times the intensity of 120 decibels, which is 10 times the amount that makes the average person hurt. So, but now, what is the ratio of intensities between the jet and the whisper? Well, to get the difference, so what is the, well, okay. We're going back. We know what the difference is, because we know that the jet engine is 130 decibels, and the whisper is 20 decibels. So now we're going backwards. We want to find the ratio. So here we start with the difference. And we know that this difference is equal to 10 times the log of the ratio. That was the previous slide. So for here, now we just solve for the ratio. So subtracting these two quantities, and you can forget the dB, it's basically a unitless quantity. 130 minus 20 is 110. Now divide both sides by 10, I get 11. So I get this equation right there. And now all I have to do is clear the log. How do I clear the log? Yeah, so this is using the inverse functions of exponentials and logs in reverse. To clear the log, I take 10 to the power of both sides. Okay, and that clears the log on the left. So I get the ratio on the left is going to be 10 to the 11th on the right. So the intensity of the jet is, and now if I plug this into the actual, what we know, we knew this was 100 watts per meter squared. I'm sorry, no. This was 10 to the minus 10 watts per meter squared times 10 to the 11th gives me about 10 watts per meter squared. So the jet engine is giving you an intensity of about 10 watts for every square meter of window that it's going through. At that distance away, 50 meters. Questions? All right, so we'll have more time to deal with that. You know, I'm almost out of time and I'm almost out of slides. But because I've kind of been rushing through these, I'm going to spend a little bit of time on Wednesday just going over this again. Just because this is so important. You really need to get it. So I'm almost out of slides, so don't worry. The end is in sight. So signal intensity is directly proportional to the power of a signal. So we often write the difference in signal levels in terms of power. So if I have two signals, the power is proportional to the intensity. So the ratio of the power levels is proportional to the ratio of the intensity. So I might as well take the ratio of the power levels. And that could also give it to you. So the power levels might be given in watts or, say, milliwatts. So if I have a signal being transmitted with a power of 10 milliwatts, that's MW, through a communication line. So this is actual electric power going through throughput. The strength of the signal at the other end is 5 milliwatts. So it started out as 10 milliwatts, but at the other end it's 5 milliwatts. So there's been some dissipation in power. What is the loss of signal strength in decibels? So you take the ratio of the output power divided by the input power. So that's 5 over 10. That's 1/2. Take the log of that. Well, 1/2 is less than 1. So when you take a log, a common log of something less than 1, you're going to get something negative. So you multiply by 10. So you get about 0.03 minus times 10. You get a loss of about 3 decibels. So cutting the power in half, or cutting any signal strength in half, corresponds to decreasing by 3 decibels. Conversely, doubling the power corresponds to increasing by 3 decibels. So this is a good rule of thumb. 3 decibels corresponds to either having the power if it's a decrease or doubling the power if it's an increase. So you often talk about the 3 decibel cutoff. This is when the actual power at a certain frequency is half the peak power. That's a good way. That's a good measure of when the thing cuts off. So this is a good rule of thumb. 3 decibels corresponds to roughly doubling or halving the power, depending on what's positive. All right, I got to go a little bit over, but we're almost done. So differences in signal levels can also be viewed in terms of voltages. So if I have a voltage going across a resistor in a wire, the power being dissipated is proportional to the square of the voltage, the resistance being constant, say. So if I have 2 voltages, the ratio of the power is going to be the ratio of the voltages squared. So the decibel difference in power is the ratio of the powers, but that's the ratio of the voltages squared. Now, using the power rule, this 2 comes outside, and the 10 turns into a 20. So to get the power level difference in decibels, if you know what the voltages are, you could do it directly from the voltages by taking the ratio of the voltages, taking the log, but now you multiply by 20 instead of 10. So, and I think, I think is this the last slide? Yeah, that's the last slide. Good. So here's just a couple of common signal references. So commonly used reference level for power is 1 milliwatt. And so the decibel units you get are called decibel milliwatts. So it's whatever the power is in watts or milliwatts, divided by 1 milliwatt. That's the reference that's the reference power. Okay. And so the power level you get out of this, when you take the log to multiply by 10, is the number of decibel milliwatts. I think we're actually trying to phase out this terminology. And a commonly used reference level for voltage is 1 millivolt. So the decibel difference in millivolts is whatever the voltage is divided by 1 millivolt. It'll beep in a second, don't worry. Okay. This gives you the voltage level. And if you take the difference of these, that'll give you the voltage voltage decibel difference. To get the difference in power, you would double that, because here you're multiplying by 10. But to get the power difference level, the difference in power levels, converting from voltages, you would multiply that by 2. All right, so I'm over time. Thanks for bearing with me. Any questions before we break for lunch? So when you come back, I know you have a short time this afternoon. When you come back, I will have the first assignment ready for you. And questions will be marked as either practice or they'll be given point values. The ones that have point values you will hand in on Wednesday. The ones marked practice or something else, that's just for your own practice. Yes, question.
Will we see the answers to the practice ones so that we're doing it right?
You will see the answers to everything.
Okay.
Practice, points eventually. Yeah. You won't. Today you won't see the answers to practice today, but you will see them eventually. Okay. All right. Thank you all. So we reconvene at 13:30. It's okay with me if you're a few minutes late because we ended late. So. Say no later than 13:40, let's say.